Hi, today I would like to talk about the basic searching technique focusing on the local search. So what is meta-heuristic? Meta-heuristic, it is an iterative generation process which guides a subordinate heuristic by combining intelligently different concepts derived from classical heuristic, artificial intelligence, biological evolution, natural and physical science for exploring and exploiting the search space using learning strategies to structure information in order to find efficiently near optimal solution. So this is defined by Osman and Kelly in 1996. Let us review local search. So local search is local neighborhood search, but usually we call it local search. So we start off with a complete solution and improve it, or we gradually construct a solution, make our best move as we go. So we need a number of move operator, take a state S and produce a new state S prime. So when we produce a new solution, a new state, we have to evaluate this new solution. So we can tell if we appear to be moving in a good direction. So let's assume we want to minimize this function, that is, we want to minimize the cost. So be careful, local search does not guarantee optimality. So local search is actually a meta-heuristic for solving computationally hard optimization problem. So can be used on problem that can be formulated as finding a solution by maximizing or minimizing a criterion among number of candidate solutions. So algorithm move from a solution to a solution space of candidate solution, that is search space, until a solution deemed optimal is found or a time bound is elapsed. So local search algorithms start from a candidate solution and then iteratively move to a neighbor solution. How to move to a neighbor solution? The move is defined by the neighborhood structure. So the neighborhood structure will modify the current solution to create a new solution that we call neighbor solution. So this is only possible if a neighbor relation is defined on the search space. That means in order to use local search, we must define how to generate a neighbor solution. So how to generate a neighbor solution is the neighbor solution is generated using neighborhood operator. So the neighborhood operator can be just a simple move, a swap, two swap. That means we take 2 points and we swap to get a new solution, or we swap a group of what we call a group of points to get a new solution. So we have to define. In order to apply local search, we must define what are the neighborhood operators that we will use to search. So the application are planning, scheduling, routing, configuration, and many more. So in fact, many or most large operation research problems are solved using local search method. For example, airline scheduling problem. So let's see this analogy. Find the lowest cost solution. So this is example of hill climbing, or sometimes we call descending, hill descending. But usually we call hill climbing, although it is searching for minimization. So let's climb down on the hill. You see that? Because this hill climbing algorithm only search for better solution. When it track here, you can see that no or better solution here. So we call it the local search trap in local optima. So how can we escape? There are few ways to escape from local optima. You will learn it later in another topic where we will use like simulated annealing to escape from local optima. We can use many other approaches. We can use taboo search, we can use genetic algorithm, we can use great deluge algorithm, and many more algorithms that can help to avoid from trapping in local optima or to escape from local optima. So these are the steps in local search. Very simple. You select initial state. So the initial state can be randomly selected, or can be randomly generated, or can use a certain heuristic to generate initial solution. So when we have initial solution, we make local modification to improve the current state using neighborhood operator. So this step is repeat until the goal state is found or the time found, or the number of iteration found. So when we do local search, we need to define how long we want to search, how many iterations that we want to search, how to stop the search. So the requirement for local search, we must have initial solution, regardless of any method to generate initial solution. So the local search starts with given an initial solution. So the initial solution is often randomly generated, or even valid, or sometimes it's just randomly generated without guaranteed feasibility. You can start with an unfeasible solution. Then we evaluate the quality of new solution. So move to other state using well-defined neighborhood function. These are the requirements to apply the local search. So what is a generate and test? It's very simple strategy. Just keep guessing. Do while goal not accomplished. Generate a possible solution, test solution to see if it is a goal state. So the heuristic may be used to determine the specific rule for solution generation. For example, let's say a traveling salesman problem. Travelers need to visit n cities. We know the distance between each pair of cities. We want to know the shortest road that visit all cities once. For example, if n equals to 80, that means we have 80 cities, then we take millions of days to solve it exhaustively. That is 80 factorial. So in TSP, given n cities with xy coordinate, select any cities as starting point and ending point, arrange the n-1 city into a tour of minimum cost. So this one is called constructive heuristic. So the representation is an arrangement of n-1 city. So we apply a move operator. We define what are the move operator that we use. Let's say swap two position. This is called 2-OR. Take a subtour and reverse it. So how big is the neighborhood of a state? We need to define how big the neighborhood of a state. Similarly, in our housing area, who is our neighbor? So we can define our neighbor can be those who are in the same road. We can define our neighbor, those who are close to our doors. Maybe 3 doors, maybe 5 doors, maybe 10 doors. So we can define our neighborhood area. And how big is the state space? What dimensional space are we moving to? What dimensional space are we moving through? So Then we need the evaluation function to calculate the cost or the quality of the obtained solution. So this is local search. When we apply neighborhood operator, we improve the solution, we improve the current solution. This is called the local search. Let's see example of a move operator 2-op. So this for TSP example, a tour starting and ending at city number 9. So we start with city number 9, then next is city 1, followed by 4, 2, 7, and so forth, until we visit all the cities and back to the city. So this example for the tour, for the initial tour. Then we apply 2-op, a 2-op operator. So let's say we randomly choose 4 and 6. So we randomly choose 4 and 6. We just swap these two positions. So when we do this, we need to break this connection. So we need to break this one, and we need to break this one. We need to break 6 connected to 5 and 6 connected to 8. So we break this point. We also break to this point. So the rest are same. So what we should do is we join the new cities. So we start with 9, 1. And now instead of 4, we connect to 6. So 6 after 6 is 2. So we connect to 2. And the rest continue. Then we start with 5. 5 connect to 4. And 4 connect to 8. So this is the new solution. So when we get new solution, we calculate a new objective function or the new tool. What is the cost of the new tool? So example of local search approach. So some local search approach are hill climbing, or sometimes we call steepest descent or descent heuristic. We have tabu search, we have simulated analysis, we have great deluge, variable neighborhood search, genetic algorithm, and many more local search algorithms. So what is simple hill climbing? Hill climbing use heuristic to move only to states that are better than the current state. Always move to better state when possible. The process ends when all operators have been applied and none of the resulting states are better than the current state, or the stopping condition is met. So in simple hill climbing, the neighbor solution is randomly generated. So at one iteration, only one neighbor is evaluated. For one neighbor is generate, evaluate. If it is good, then we accept. If it is not good, we randomly generate another neighbor solution and evaluate it, whether we can accept the new solution or we just discard that solution. So we will accept only if the new solution is better than the current solution. This is analogy of simple hill climbing optimization. So we are looking for a better solution. Let us proceed with a traveling salesman problem using hill climbing algorithm. So define the state space as the set of all possible tours. Operators are exchange the position of adjacent city within the current tour. Heuristic function is the length of the tour or the cost of the tour. So we start with initial tour, where we start, the initial tour is city A to B to C and D. So let's say the operator is swap two adjacent cities. Let's say we randomly generate the point to swap. We got point 2 and 3. So point 2 and 3 is B and C. So we swap these two positions, B and C. So we got A. You swap B and C, we got A, C, B, D. So we evaluate this. If the new solution is better than this one, the initial solution, then we accept this solution, randomly generate a new neighbor solution from the current solution. Let's say we randomly generate, we got this solution. Then we evaluate the new solution. Is this better than the previous solution? If it is better, then we accept and make another move operator. Make another neighbor solution. So let's say when we evaluate this, the new solution is not better than the current solution. So we reject this solution and randomly generate another solution. Let's say we generate this solution. The process is continue until we end with stopping condition. So the stopping condition might be when there is no more better solution, we start in local optima, or the number of iteration reached, or the number of the execution time ends. So we need to define how long we are going to search. So potential problem with simple hill climbing. We terminate when at local optimum. That is, get stuck at local maxima or local minima. So the order of application of operator can make a big difference. That means when you start, where in the solution space that you start the search, or what are the random number that you generated first. So the order of application of operator can make a big difference. If you are lucky, you search at the good area, then you may find a better local optimum. If you unlucky, you start with bad area, bad space. If you start with bad solution space, you might end up with a bad local optimum. So possible solution, try several runs starting at different position, increase the size of neighborhood. For example, in traveling session problem, you can try 3 op rather than just 2 op, or you can use multi-neighborhood operators. So let's have a look on the analogy of search strategy visualization. So let's say we are searching for the highest mountain. So let's say we start here because this is the highest mountain at this local area. So that means we thought that this is the highest, because when you go down, the solution is lower. So let's say another one, you start here, you go this mountain. You start here, you go this mountain. If you start here, you go this mountain. But if you are lucky, you start from here, you get highest mountain. So we do not know. In local search, we do not know where is the optimum solution, where is the highest mountain. So without anchor point, the behavior of the ping trajectory is hard to be explained. For this diagram, do several local search runs with different configurations. Record diverse local optima or anchor point. There we will circle the anchor point. So these are the local optima. So with anchor point, the behavior of the ping trajectory is as follows. Trap in region that contain red and blue. This is the anchor point. That fail to visit good solution. So the green or orange anchor points is the better solution. So the behavior of the pale blue trajectory is as follows. After reaching the local optima, it diversifies to another place. It managed to reach green and orange anchor it managed to reach green and orange anchor points, and thus its performance is better than the pink trajectory in figure 3. The steepest ascent hill climbing. A variation of simple hill climbing. Instead of moving the first state that is better, we move to the best possible state that is one move away. So steepest descent is a variation of steepest descent or steepest ascent. For hill climbing, that means maximization problem, because steepest ascent hill climbing. For those minimization problem, we call steepest descent. So they are the same, but one looking for the highest or maximum value. The other one, steepest descent, is looking for the minimum value. So in this algorithm, instead of just generate one neighbor solution, evaluate it, and accept or not accept, this steepest descent algorithm, we generate all the possible neighborhood, all the possible neighbors. So it will accept the best neighbor among these neighbors. So the order of operator does not matter, because at each iteration, this algorithm will generate all neighbors. So not just climbing to a better state, it climbing up to the steepest slope. So not just climbing to a better state, this algorithm climbing up to the steepest slope. Hill climbing termination. What is local optimum? All neighboring states are worse than or same the quality of the solution. What is plateau? So plateau is when all neighboring states are the same quality as the current state. Heuristic dependence. Hill climbing is based on the value assigned to state by the heuristic function. The heuristic used by hill climbing algorithm does not need to be a static function of a single state. So the heuristic can look ahead many states or can use other means to arrive at a value for a state. So let's say the steepest descent heuristic. It starts from a random configuration. At each step, we move to the best neighboring configuration. We stop when it is no longer possible find better neighboring configuration. This is called local minimum. So this is the illustration of the steepest descent heuristic. So G is the global minimum, L is the local minimum. So this is analogy of steepest descent cases. So let's say we start here. So we go down to the lowest slope. If we start here, we go down to this. But if we start here, we start in the plateau area. Okay, we have done the hill climbing algorithm. So this is the assignment, next assignment for you to complete this topic. Okay, that's all for today. Thank you very much. Bye.